let's talk about the swing lab.
Okay. So, like, when we're talking about, like the period, you know, like, what do you guys think had the most impact? 'Cause, like, you and I both did it together, and I'm, like, a lot heavier than you. But
yeah,
we basically...
but we were synchronized the whole way.
Yeah.
But I feel like it was because once y'all got going, y'all, like, your body position became, like, similar.
Yeah.
So then you were able to have, like, the same.
And our
Yeah,
amplitude
swing.
was the same the whole way.
Yeah.
Even though I started like a little earlier than hers, she caught up eventually, like after a swing or two.
Yeah.
I feel like it's because the swings had, like, the same length, like, chain, you know? So, like, like, if you're thinking of that as, like, the lever, like, whatever it says, like, so that's the same. And then, like, the way we were moving our bodies, like, that, like, I can't even do
And
it.
y'all
but,
started
like,
at the
it's
same
also
angle.
the same.
Yeah.
Yeah, so I feel like since there's so many things that we're saying, that's probably part of it. And, like, us changing the rotation, like, that's...
Yeah, and
torque,
mass was
yeah.
just the small part.
Yeah, like, mass wasn't really as important as, like, us changing the rotation the same way, which I think would be, like, the same torque and stuff like that. So, and then, like, the starting height, like you said, was similar.
So I feel like we need to answer these questions. Like,
Okay.
So the first one is, when you swing at the park, which of the above characteristics plays the greatest role in determining the period of your swinging? Why? Which is the second most important? Why? So what did we decide about
I
that?
think the starting position plays a really big role, and then the length of the swing also plays a really big role.
Yeah, I agree.
Because it's the same distance traveled.
Right.
And
Because, like, if you're traveling it, like, that's, like, that changes it. Like,
Yeah.
it's like one of those, like, Newton cradle thingies, you know, where you, like, do the ball
Yeah,
and
the
it goes
ball
like
and it all
that.
goes.
Yeah, it's what makes me think of. I don't know why.
I get that.
And the starting position, it's the period of swing. It depends on where you start, and then gravity plays an effect, so we all get pulled down at the same time.
True. Okay, what's the next question?
Which of the three characteristics above? So those are, it and your mass, the length of the swing, so the lever arm, and your starting position when swinging, when varied, had the greatest effect on the period of the swinging.
The
So-
mass definitely didn't have an effect because we're different masses.
Yeah, and then it was still the same synchronization. So I would say length of the lever arm.
Okay.
Yeah,
Yeah.
I think so too. Cool.
I agree with that. So,
Okay, so the last question.
To verify that changing the mass has no effect on the period of swinging, have the lightest and heaviest person of your group swinging side by side. It's
Yeah, that's what we
relatively
did.
easy for the two swingers to synchronize. Why? And
It
me and
was.
Tara went, and yes, because the two began to move in the same position, it was relatively easy.
yeah.
Yeah.
All right.
Oh, there's so many ladybugs.
I know.
Hi, Miss Cornell. There's
Aw.
a lot of ladybugs. Look. Okay, so what's our first question?
So, there's a ladybug. Okay.
Oh, there's
So-
another one.
Given that the class bully weighs twice as much as you, how can you change how you sit on the teeter-totter so that you both balance where he sits on the other end? So what we thought was you can sit on the very edge while the bully sits closer to the center of rotation, so it evens out, and then
Yeah.
the torques will be closer to equal.
Yeah, so like in equilibrium with each other. And oh my gosh, wind. The outdoors. Okay. So for our teeter-totter, it is like really hard to find like an actual
Yeah.
teeter-totter. So the one that we found had like the fulcrum up top. So we could only like move so much to get closer to the center. So when we did it, like, I am the group member with the larger mass, and so it was definitely hard for us to get it going and get it balanced because like we calculated our torques.
So my weight was 135 and my force was 601, and the lever arm we calculated was, we measured, and it was 1.45 meters. So then when we multiplied the force by the lever arm, my torque was 871. and-
0.45.
Yes.
And then my weight is like 40 pounds heavier than her, and so my force was 780 newtons. And my lever arm was the same though, since we couldn't really move. So my torque was 1,131 newton meters. So obviously we weren't really able to balance it. But we just kind of looked at the numbers and figured out that if I could have moved closer, then my lever arm would have been a way smaller number. So when you multiplied, I could have lowered my torque a little bit. So that would have, if we could have done that, it could have evened out, and then we probably would have balanced a lot better. So that's kind of how it should have worked.
Yeah.
Yeah, and so I guess the last question is, what can you say about the sum of the torques exerted by the two group members on the teeter-totter? Okay, I mean, you want them to be equal.
Yeah, so
Yeah.
you want to try to make it where you sit closer to the
Yeah, or the heavier person's closer to the center of rotation, or like
then
to the
it will
fulcrum.
even out.
Yeah,
And yeah.
that's about it.
So,
yeah,
yeah.
that was fun. We like almost hit a bunch of kids accidentally.
Yeah, we got them to video us.
Yeah, that
They're
was
probably
nice.
like, why are you here? Like,
Yeah, and now there's all these
Yes.
ladybugs, but it's fine. They're cute.
yeah.
But, look at my nails.
So we timed it, and it looks like our average is around, we have 248, 258, 237. So the amount of force that was applied seems to be the same each time, so we can say that that's safe. And I noticed that when she started walking towards the center, that the outside started slowing down, and I think it's maybe because like the center of gravity was there, and I guess if she's walking towards it, like the weight and like the force of her weight on the outside make it go faster. I don't know, I just need to look over the data again, but yeah. Okay, so from the merry-go-round, we concluded that even though that I was affected by the force of the merry-go-round going in a clockwise direction, it did not affect the ball. that was a separate part of it, and it ended up hitting the ground in the same place each time. When I dropped it, it didn't end up traveling with me and going clockwise in the other direction. So yeah, the only force that we concluded acted upon it was gravity.
Talking about the merry-go-round today.
For our playground physics lab.
So what would happen if your feet slipped while you were spinning around? Would you fly off from the center of the merry-go-round? Would you continue in a straight line? Would you fall towards the center?
And we said you would fall in a straight line because tangent to the merry-go-round is in the same direction. And so we have arrows that we drew on the diagram, and it showed like the trajectory of the ball after we released it from the merry-go-round. And then from the perspective of the spinning merry-go-round, what are the forces on the balls as the merry-go-round turns?
Well, from the perspective of the server, it would be angular momentum because the merry-go-round maintains a constant speed. And from the perspective of the merry-go-round, it would be inertia because the ball maintains the same speed.
And so then our other question is calculate the average periods for halfway and all the way out from the columns above, and then what happened to the period of revolution when the person walked towards the center. So it takes a shorter amount of time to travel because the angular momentum depends on the moment of inertia, which is the distance away from the center, and the speed at which the person was spinning. So in the experiment, the radius decreases as the person walked towards the center, and so then our other question is, did the speed decrease, stay the same, or increase, and how do you know this?
And our speed increased as the person walked towards the center.
Because that's where the center of gravity was for that. And then if the angular momentum is to be conserved, it won't change as the person walks towards the center. The distance from the center has decreased in doing so. What must happen to the person's speed then if angular momentum is to be conserved? Did you observe this?
Well, as the merry-go-round decreases speed, the angular momentum is conserved, and yes, we did observe this.